Brief introduction. Thanks, Francesco, of having me here. Yeah, it's a pleasure for me to be, after 2 years absence, to be back in Italy for a conference. I used to work in Stuttgart. Since March, I started as an associate professor at Eindhoven University of Technology. So I moved to Netherlands, and for that reason, I haven't attended so many conferences in this year as well, because I had to tell to my wife, yeah, I cannot move another time the country and then go every 2 months on vacation without her. So yeah, but now I'm here, enjoy the weather and the food, and I will talk today about my most loved topic, nonlinear beam formulations. Quite an old topic, but still plenty of things can be done in there. So I will present the work on a total Lagrangian Petrov-Galerkin Cosserat finite element formulation, and we were actually inspired by a paper of Sonville and co-workers who formulated Cosserat theory exclusively on an SE3, in a SE3 framework. They treated it also numerically in the SE3 framework, and the elements performed very well. However, you have to go all in with that formulation, so you need all your solvers have to be in that framework, and my goal is rather to include nonlinear rods into a multi-body dynamics framework using standard solvers, standard ODE solvers or standard DIE solvers to get the solutions for dynamic responses, and therefore we were looking for another way to do. So we wanted to have this finite element formulation with the SE3 interpolation, which I will present in this talk, but outside of the Lie group framework, which means we have to make the choice of a parametrization of our Lie group, which was done with a rotation vector parametrization. So part of it, the rotational part, is parameterized by rotation vectors. And to simplify certain things, we opted for a Petrov-Galerkin projection method. So to set a little bit the notation, let's start easy with the kinematics. So nonlinear rod is actually described by a centerline curve. So that is just a curve in the three-dimensional space. And then the rigid cross-sections are attached to that curve, and they are usually represented by the cross-section orientation, which is here this transformation matrix, which takes a representation of a vector in that cross-section fixed frame to an inertial frame. So if we have a look at point Q and we consider our rod as a three-dimensional body, then we can go to that point, or we can describe that point by the vector chain of first going to the center line, and then from the center line we go to the point that is a constant in the cross-section fixed frame, and it is depending on the referential arc length S on the change of orientation. So that is a transformation matrix. And with this kinematical fields, we can then describe by taking the variation, the virtual displacement, and also the virtual rotations. And if we take the spatial derivatives with respect to the arc length, we can define the strain measures, which are dilatation and shear. And for the change in orientation, we have bending and twist of our beam. Then the statics is as commonly described from the variational principle, the principle of virtual work, which states that the internal plus external virtual work has to vanish for all virtual displacements and all virtual rotations. So basically what you see here is a little bit more an elaborate form of the variation of, at least in for a completely elastic material, as the variation of a strain energy density, which depends only on the previously introduced strain measures. And then we have the external forces where we have line distributed forces, line moments, and on the boundaries we have forces and moments that can be applied to the beam. So very standard so far, nothing new. And then how do we get to the finite element formulation? Yeah, usually that is, if you start from the principle of virtual work, it's quite straightforward. We just have to discretize the virtual work principle. However, everybody who did that knows that there are some pitfalls, and yeah, the detail lies in the devil. And what we've opted here is for a Petrov-Galerkin projection method, where we use an independent field for the test functions. And it was actually used the first time in rod theory by Jelenic, who was also thinking that it was for his shape function or his ansatz function he has chosen, it was too tedious to do the test functions. And so basically what we do is we have to approximate the two kinematic fields. One is the center line, the other one is the orientation. And the only thing I say so far is that for the position we take nodal positions, and for the orientation we take nodal orientation vectors. So nodal rotation vectors. So if you have these three unknowns of the rotation vector, then we get the orientation matrix, the orthogonal matrix, back by the exponential of the SO3 group. The test functions are then used just by linear Lagrangian interpolations. So I will present the two-node element, and the only way to then come up with some test functions is to linearly interpolate those. So we have then the virtual nodal rotations and nodal displacements. And then the integrals are approximated by Gauss quadrature, and when we then insert that into the continuous virtual work form, we end up with the nonlinear equilibrium equations that we can solve with a Newton-Raphson scheme. Just as a reminder, yeah, what would it mean to go with the Bubnov-Galerkin projection method? That ansatz function, and we do a consistent variation of that. And also the virtual rotation, there we have to take the variation of the orientation matrix and then pre-multiply that with the orientation. Yeah, particularly for that case, it's very easy if we are just linear or if you have just Lagrangian interpolations. But we will come here with a highly nonlinear interpolation, and then these variations, they become extremely complex, computationally expensive though, and what is also quite nice, or what is troublesome, is they become different for each ansatz. And that can be resolved with the Petrov-Galerkin. I will present today only one interpolation, but in fact we came up with an entire family of different ansatz functions that can use the same test functions. And so it becomes very interchangeably, and you don't have to do the calculus again and again. So the SE3 interpolations from the special Euclidean group was introduced by Sonville for the geometrically exact beam finite element formulation. And yeah, in contrast to what we have come up with, a slight difference is that the virtual displacement is in the body fixed in the cross-section fixed frame in their framework that is natural in that SE3 formulation, and they've had a Bubnov-Galerkin projection. And as I've mentioned at the beginning, they need very special Lie group solvers to solve their Newton-Raphson, so to resolve their nonlinear equations, the static equations, but also for the dynamic equations, they have to come up with an SE3 generalized alpha method. So, but maybe for people who are not familiar to the SE3 structure, where is it in the rod formulation? We will go back to the kinematics of the rod, where we address the point Q with respect to the origin, to the inertial frame. And so we have here the center line plus cross-section orientation plus this relative vector between cross-section, between the center line and point Q. And if we add here a 1, so that is actually an affine transformation. If we add here a 1 at the bottom, go to 4 dimensions, then we can rewrite this affine transformation as a linear transformation, which is called a homogeneous transformation. And what one can think of is actually what this here is. This here is the representation of point Q with respect to the frame K, calligraphic K. What I mean with the frame is we take P as the origin and the orientation of the cross-section fixed frame as its coordinate system. And if you want to have a transformation of that representation with respect to the calligraphic K frame to the I frame, then we have in here that homogeneous transformation. And one can show that this has nice group structures, so we can easily introduce also another intermediate frame, K0, and then can just concatenate the entire thing. So you do the same thing that you know from rotations or orthogonal transformations, where you have the multiplicative decomposition. You do it also for SE3. And that's what we're going to use for the interpolation. So the interpolation is a 2-node interpolation. We have as unknown the position of the center line here and the position of the center line in node 1. We know with the rotation vectors psi0 and psi1 the orientation here and there. So we can construct our Euclidean transformation matrices in point 0 and in point 1. And then we can look for the relative Euclidean transformation by just doing the math respecting the that it is a matrix Lie group, and then we get the relative Euclidean transformation between point 0 and point 1. And from that we can extract so-called twist vector, which represents or parametrizes this SE3 group. So if we insert then such a twist vector again into the exponential, then we will get back a homogeneous transformation. And that's how we construct this interpolation. So we start basically at the node 0, and then we include here this homogeneous or Euclidean transformation that we scale with the arc length f. So here it's just one element for the entire beam. So if it's at 0, then we are at the beginning. Then the twist vector is 0, and the exponential will be the unit matrix. And if we are at 1, then we will get back the relative Euclidean transformation, and we will end up at the Euclidean transformation at node 1. And in between, it's just a highly nonlinear interpolation, a coupled interpolation, and if one carries that out, for the orientations, what one sees here is the usual SO3 interpolation that one knows maybe already from Crisfield and Jelenic proposed that in 2001. But what is somewhat special is that in here also the center line is extremely nonlinear, and if you now think of taking the variation of that, you know that you don't want to do that. So the nice thing about this interpolation is the following. Certainly it preserves objectivity, which should be something that each interpolation should preserve. And what is very special for that, it is actually a constant strain element. So It's a two-point element, and it represents constant strains. That means this formulation is intrinsically locking free. So we can make our rods as thin as possible, and there will be no locking at all, neither membrane locking nor shear locking. And then the particular way we did it with Petrov-Galerkin, and it is total Lagrangian and also singularity free without anything to do in statics. So then one can do the helix example where we have two torques at the end of the beam. You see here the slenderness, and the solution is not at all affected to it. And by the way, the helix is a constant strain solution, and that is a constant curvature solution here. So it is actually not a very good benchmark example, because you really you will get the exact solution even with the interpolation. But also all other benchmark examples are passed quite well. Also, if you have non-constant strains along the beam, then certainly because you have constant strains, you need a higher resolution if you're really interested in the strain distribution. Otherwise, if you are more interested in the displacement, then also coarser resolution is fine as well. So now let's add some dynamics. So yeah, then the centerline curve and the cross-section orientations become explicitly time dependent. So we can define, in analogy to the positional derivatives, also centerline velocities by the time derivative, and also the angular velocity, which will also have representation in the cross-section fixed frame. And now comes the peculiarity of our formulation, where we have to choose somehow how to get these or how to interpolate these velocities. And if you have a look at the inertial virtual work, then we have opted already for the virtual displacements and virtual rotations to be linearly interpolated. And in case we want to have a constant and symmetric mass matrix, we have only one choice left. So we also have to linearly interpolate those. Otherwise, we would end up with a non-symmetric mass matrix, which is possible, but coming from dynamics, something that I don't enjoy too much. If you have a look at the paper of Crisfield, for instance, he used the Petrov-Galerkin approach, but then has connected here this velocity to the nonlinear interpolation. So he really computed the consistent time derivative with respect to his ansatz function. That's something we don't do here. So the connection in between the position field and the velocity field is not given yet. So that has to be given, and we do that on a nodal level. So on the nodal level, we relate the time derivative of the nodal positions and the time derivative of the orientation vectors, the rotation vectors, with the nodal translational velocities and the nodal angular velocities in the cross-section fixed frame. And what comes here is that for an orientation vector, rotation vector that exceeds 2 pi, that becomes singular, that mapping. And there is a way to resolve that. One can jump back and forth between the rotation vector and the complement rotation vector, which is basically one times we measure the angle from that side and then we measure it from the other side. And that's one way how one can resolve it. Nowadays, or 1 year later, we proposed to use not rotation vectors, but unit quaternions on a nodal level. Then we don't have any singularity problems at all. What is interesting is then that we end up with an ODE structure in a first order form, where we have here the kinematic differential equation on a nodal level, and at the bottom we do have the dynamics, where we have the mass matrix and the internal, external, and the gyroscopic forces. And in that form we can use general ODE time integration schemes to go forward. And let's see if, yeah, it works like that. So to see that also really the dynamics is captured, what you can see here is a Wilberforce pendulum with 3 coils, and it's a nice speed phenomena where you see an interchange in energy between a longitudinal oscillation and a torsional oscillation, and which gives us some insights that also the dynamics is quite reasonable, even though it is extremely difficult to find very good benchmark examples to benchmark dynamics. Statics, we have way more analytic solutions that we can compare to. Dynamically, I'm still a little bit, I'm still looking for good examples where we can really benchmark our formulations. And I will quit, or I will end this talk putting you a smile on your face with the optimist. It's kind of a toy I have on my desk, and I was always suffering that I couldn't compute that, and yeah, now we can finally do that. And
all these for them.
I did, yeah, you do it for a bigger purpose, like solving medical issues. I just do it for computing toy examples. Yeah. Thanks for your attention.